Welcome to Math466, Lecture 21. We're now shifting to random matrix theory. So since we're shifting, I thought it would probably be a good idea to review basic linear algebra, especially linear algebra related to eigenvalues. Because I think it's been a while since a lot of you have seen the proofs and the arguments.
It's
50 RBIs in a month?
Yeah.
Yeah, 50 RBIs in a month I can believe.
There's still a state record of 60.
Yeah, that's fine. But they don't let just anybody be a baseball professor. All right. So review of eigenvalues. So what I want to do is I want to go over how do you find an eigenvalue, what is an eigenvalue, how we can choose better bases or coordinate systems for our operators. So this is supposed to be in some sense like a capstone class where we go back and revisit the math you've seen. You should view a matrix as a representation of a transformation in a given basis. So if you choose a different basis, the matrix will look different, but it will be the same operation. So whenever there's a matrix, there's actually two bases you have to specify: the basis of the input space and the basis of the output space. Typically, we take those bases to be the same, and we typically take them to be the standard vectors, E1, E2, E3, E4. But they don't have to be. If I give you an operation that stretches by a factor of 2 in this direction and contracts by a factor of 1/2 in this, well, I probably want to choose my bases to be like this. All right, so typically, vectors have magnitude and direction. If you apply a matrix on a vector, you typically get back a new vector. If you happen to get back a vector that's in the same direction but just rescaled, then you say that V is a eigenvector and lambda is the eigenvalue. And we always assume V is not the zero vector. Because if V is the zero vector, then any lambda works. And so this gives us the eigenvalue lambda, eigenvector V. And so you can write this as AV minus lambda times the identity of V is the zero vector. So just multiplying by 1. So this is the same as A minus lambda I acting on V equals the zero vector. So this means V lands in the null space of A minus lambda I. So because I'm having AV equals lambda V, A must be a square matrix because the vectors on the two sides have to have the same dimensions. So A is a square matrix. I can write down the identity. All this is justified. How do you tell if the null space is non-empty? So I want to try to solve, now there's always something in the null space. Give me something that's always sent to 0 by a matrix. 0. The null space is a vector space. We know the 0 element is in the null space. Is there anything other than the 0 element in the null space, or is the null space boring? How do you tell if the null space is non-empty?
Number of eigenvalues. Right? The number of non-imaginary eigenvalues.
Not quite.
Well, if you get solutions for lambda, it will be non-empty.
So if you can find such a lambda, but so how can I tell? So B is a square matrix. Is the null space of B more than just the zero vector? There's a very simple condition to tell you if the null space is more than the zero vector. You take a certain quantity associated to the matrix.
The inverse.
Well, if B is invertible, I want to solve BV equals 0. If B inverse exists, then we would get B inverse BV equals B inverse of 0. B inverse of 0 is just 0. And so if B is invertible, the null space is just the zero vector. So how do you tell if a matrix is invertible? If the determinant. So if the determinant of B equals 0, then it has a non-trivial null space. Else trivial. This is wonderful. This is a really simple condition to tell when is the null space more than just one vector. So for us, we want to look at the determinant of A minus lambda I. And this will be a polynomial of degree n in lambda if A is n by n. Okay? So this is the simple test, and this is how you can find the eigenvalues. So by the fundamental theorem of algebra, we have n roots. If the n roots are distinct, then we will have n distinct eigenvectors. Each eigenvalue corresponds to at least one eigenvector. If some of the eigenvalues are the same, however, we might not have a full set of eigenvector directions.
Couldn't you get eigenvalues which are 0?
You could get eigenvalues which are 0. That's fine. And they could still have a non-zero eigenvector associated to it. So for instance, imagine I give you the matrix 1, 0, 0, 0. It acts on the vector 0, 1 and gives you back 0 times 0, 1. So the vector 0, 1 is an eigenvector with eigenvalue 0, but it's not the 0 vector, so everything is okay. So the problem is, for instance, if I give you the matrix 1, 1, 0, 1, let's look at this matrix. So its determinant, so the determinant of 1, 1, 0, 1 minus lambda I, this is the same as the determinant of 1 minus lambda, 1, 0, 1 minus lambda equals 0. So you get 1 minus lambda equals 0, so you get lambda equals 1 and 1. You have a double root of 1. And it turns out this only has one eigenvector direction. So if I want this to basically equal xy, what must be true?
Y 0?
I'm sorry?
Y 0?
So y has to be 0, because if y is not 0, we would get x plus y over here. So y has to be 0. So anything of this form works. Well, they're all really the same. If I take an eigenvector and I multiply by 5 or by 7 or by 1/3, it's still essentially the same vector. So you often say, look, let's take an eigenvector of size 1. Or maybe we'll take an eigenvector whose first non-zero component is positive 1. Some kind of normalization. So here is a matrix that does not have a full set of eigenvectors. So this shows you that the subject can be challenging. Okay? I'm sorry? Well, I mean, just the fact that we're looking at 2 by 2 matrices, and already we found, without too much trouble, a matrix that does not have 2 eigenvectors. It only has one direction. So it does not mean that I can decompose an arbitrary transformation in terms of eigenvectors. Now, if my matrix has n distinct eigenvalues, each eigenvalue will have an eigenvector associated to it. And then things will go well. With probability 1, if you write down a matrix, you will have enough eigenvectors to be fine. But it is possible. How many of you have heard or remember Jordan canonical form? Is this done at all? I'm seeing some hands going up.
Sounds very familiar.
Jordan canonical form. You can't diagonalize an arbitrary matrix, but you can put a matrix into Jordan form where you have these Jordan blocks. I'm sorry? No. I would never do that. Yes. I mean, I might have mentioned it with Conway's see and say sequence. So Jordan canonical form looks like this. Is you have blocks where it's constant eigenvalue along the block, then it's all 1s above, and then it's all 0s everywhere else. So any matrix can be put into Jordan canonical form. It's not as good as being able to put a matrix into diagonal form, but it's the best you can do in general. It turns out that this actually arises in Conway's see and say sequence in terms of how to do the analysis. So if you take the sequence 1, if you say that out loud, you have 1, 1. If you say this out loud, how many 1s do you have? I have 2 1s. I have 1, 2, 1, 1. I have 1, 1, 1, 2, 2 1s. I have 3 1s, 2 2s, 1 1.
Whoa. Wait, sorry, whoa.
So this is Conway's see and say sequence. If you ever have to do a non-trivial sequence, this is a fun one to do. You basically read each line out loud. You start with 1, and I read it out loud. I have 1, 1. I have 2 1s, 1, 2, 1, 1, 1, 1, 1, 2, 2 1s, 3 1s, 2 2s, 1 1. The next line would be, what is this? Would be 1 3, 1 1, 2 2s, 2 1s. Am I doing it correctly?
1 1 1 3 2 1s.
Okay, so 1 1 1 3 2 1s, 3 2s. I'm not sure if I've made a mistake or not, but maybe not. Okay, and so you can ask, how quickly is the sequence growing? And it turns out the growth is determined by the eigenvalue of a 92 by 92 matrix, which is not diagonalizable but is Jordanizable, and the largest block is in the 70s. You will never get a 4 no matter how far you go. There are 92 elements. I'm sorry? So it's a nice exercise. Prove that you never get a 4. Or if you want, prove you never get anything above a 5 or never anything above a 6, something like that. There's the cosmological theorem. There are 92 elements, and at some point in time, from that point onward, no matter what you start with, all of your sequences will have all of the cosmological elements. The original proof was lost in Conway's office, and a new proof had to be found. It was easier to find a new proof than to search the office. A lot of great mathematics behind this. I'll post some reading on this. It's a fascinating, fascinating problem, and a strange application of Jordan blocks. Why do we want diagonal matrices? Diagonal matrices are really easy to work with. Essentially, all a diagonal matrix does is it rescales each component of your vector. The best matrix, of course, is a multiple of the identity, because then it rescales everything by the same number. But rescaling each vector by a different amount, not a big deal. So if we can somehow diagonalize a matrix, that's extremely useful. All right. So when is a matrix diagonalizable? That's the big question. So when can we diagonalize? What do the eigenvalues look like? Now, it turns out in a lot of problems that have physics meaning, we have real symmetric matrices. So A equals A transpose. Sometimes we have complex Hermitian. And so for complex Hermitian, this is A equals A Hermitian. So A Hermitian means take the complex conjugate transpose. So complex conjugate transpose. So let's look at real symmetric matrices and see what we can say about their eigenvalues. So in your linear algebra class, did you guys prove anything about eigenvalues of real symmetric or complex Hermitian matrices? Right. Okay. So it turns out matrices of these forms have incredibly nice properties. So assume A is real symmetric. So A equals A transpose. Let's look at AV equals lambda V. And so if I take transposes of both sides, I get V transpose A transpose equals lambda V transpose, because lambda is just a scalar. So if I take a dot product, I would get V transpose A V equals lambda squared V transpose V. Well, V transpose V, that's just the length of the vector V. So lambda squared times the length of V. And over here, this is just the length of the vector AV. So what can you conclude about lambda squared?
Has to be 1.
I'm sorry?
Has to be 1.
Why does it have to be 1?
Or if you're scaling the vector, and the scale's not
I mean, maybe A sends V to 0. And then in that case, lambda would be 0. Right? That's a possibility. But we know, oh, sorry, these should be squared. But we know these are non-negative numbers. What would you like to conclude at this point about lambda squared? Well, lambda squared could be 0. Maybe AV is equal to 0. And so if AV is equal to 0, if V is sent to 0, then I would need lambda to be 0. But what can you tell me about the norm of AV squared?
lambda squared divides it.
What kind of number is this? The norm of AV squared. What kind of number should that be? It should be real, more than just real. Not integer. Integer is strong. It should be non-negative, right? If this is a length, it should be non-negative, and if this is a length, it should be non-negative, and thus maybe lambda squared should be non-negative.
It's squared, so
I'm sorry?
it's squared, so why would we worry that it would be negative?
Well, lambda itself could be negative, or in fact, you could even have lambda could be something that squares to something negative. So for instance, the only complex numbers that could square to something that's real, if I had, basically just pure imaginary, say I or negative I, they would both square to something real, but they would square to something that's negative. So therefore, lambda squared is in R, therefore, and non-negative. Therefore, lambda is greater than, therefore lambda is real. So the conclusion is correct, but the argument here is wrong. There's a small mistake that goes on. And so here I'm saying V is a eigenvector of A. I'm implicitly assuming that V has real coordinates. Let's take the vector 1, I. So consider V equals 1I. Then V transpose is 1I. And so if I look at V transpose V, I get 1I, 1 squared plus I squared is 0. So I just got a vector whose length is 0. What went wrong? It's possible, when we're trying to solve things using the fundamental theorem of algebra, we may have complex things coming into play. The problem is when we're taking the length of a vector, I don't do v transpose v. What I should do is I should do v Hermitian v. Because remember, when you take the length of complex numbers, you take the complex conjugate times itself and then take the square root of that. So if I do v Hermitian v, I'll get 1 minus I dotted into 1 and I. And now I get 1 squared minus I squared, which is 2. And so this is going to tell me that the length of v is the square root of 2. And if you draw what we have, here's the vector at 1i. That's 1 unit, that's 1 unit. It should have length square root of 2. Everything works out. So the proof I gave here, I can't actually assume that the length of v is not 0 if I'm doing things like this. So even though A is real symmetric, I actually need to go through the complex numbers to do the proof. So, fortunately I'm at the blackboard. Basically, search and replace all t's to h's, and then the proof is fine. What happens if I do the search and replace? Well, I now have AV equals lambda v. And so now when I take, I'll write it again so I don't go too far beyond people. So we have AV equals lambda v. V Hermitian A Hermitian is equal to, now what do I get on the other side? If I take the complex conjugate transpose of lambda v, what do I get?
Lambda v Hermitian.
Lambda, not quite. Not quite lambda v Hermitian. Almost, but not quite. So I'm taking the complex conjugate transpose of this. What do I get? I'm sorry?
Are you asking for
I'm taking the complex conjugate transpose of lambda times v. Yes, it's the complex conjugate of lambda times v Hermitian. And now the next line would be v Hermitian A Hermitian A v equals lambda squared in absolute value v Hermitian v. And now I get the norm of AV squared equals lambda squared the norm of v squared. And unfortunately, this is useless. Why is it useless? Well, I've got the modulus of lambda squared. It's really not giving me any information. The trick is, rather than trying to get to the length of AV, I don't need to have two A's here. I can just have one. And then I can have A acting on different sides. So what we'll do now is let's tweak it. Let's look at V Hermitian AV. And so the other quantity was in some sense a little bit more natural to look at. But let's look at this. If we look at this one way, this is V Hermitian times AV. And if we look at another way, it's V Hermitian A times V. Now, if we calculate A of V, what is A of V? We're assuming V is an eigenvector, so what will AV be? It will just be lambda V. So this side will just be lambda V Hermitian V. On this side, because A is real symmetric, A equals A Hermitian. So this is the same as AV Hermitian V, because A equals A Hermitian. Well, AV is equal to lambda V. When I take the Hermitian, I'll now get lambda bar V Hermitian. So I get lambda bar V Hermitian V equals lambda v Hermitian v. As v Hermitian v is the length of v is not 0, this implies lambda bar equals lambda. This implies lambda is real. So the eigenvalues of a real symmetric or even a complex Hermitian matrix are real. This is extremely useful in physics because these are supposed to model a lot of things. They're supposed to model energy levels. The energy levels should be nice real numbers. Your energy levels should not be imaginary. And this, in fact, will allow us to talk about ordering between events. Which is the lowest energy, which is the second lowest energy, which is the third lowest energy, and so on and so on and so on. So the next question is, this proves that the eigenvalues are real. What about the eigenvectors? Well, now you go back to solving, AV equals lambda v. And the question is, if you start off with a real eigenvector and a real matrix, a real eigenvalue and a real matrix, will you now have a real eigenvector? So let's go to the real symmetric case. So A is real symmetric. AV equals lambda v. Lambda is now in R. So we're trying to solve A minus lambda I acting on V equals 0. And this is a real matrix. So will we enter the complex numbers as we try to solve this? Or will this stay real? So do you remember Gauss-Jordan? Going through and trying to solve. I think you often use Gauss-Jordan to find like the inverse of a matrix, or Gaussian elimination. Are these terms at all vaguely familiar? So if you try to do Gaussian elimination on a matrix that's real, will you ever be entering the complex numbers? You're taking one of your rows, you're multiplying, you're clearing off, you have your pivots. You never enter the complex numbers. So never enter the complex numbers. So in the case where your matrix A is real symmetric, the eigenvalue will be real and the eigenvectors will be real. Everything stays real. If your matrix A was complex Hermitian, you could have complex values in here, and then you could have complex eigenvectors. So the question is it possible that you might have complex eigenvectors? I'm not sure if this pivoted enough, so I will just make sure it's there for a second. Okay. So let me give you one of my favorite matrices. Is there anybody here who is nobody here is a double major in physics, right? Because the physicists and mathematicians have different. You're not a double major, are you?
Well, Eliza and I both took physics for a while.
Wait, but you're no longer majoring in physics, right? You've realized the errors of their notation. You just can't stand that they choose to rotate the wrong way. So we have rotation matrices. What's really sad now is I have degrees in both math and physics, and I can't remember which is the right way of doing things. I know whichever way mathematicians do it is the right way, but I've been going back and forth so many times that I can't remember. So let's do cosine theta minus sine theta, cosine theta. Let me think for a second if I want to do it this way. So if I take the vector 1, 0, I'll move it up. If I take the vector 0, 1, yes, this is the right way of doing things. The other way is just putting the minus sign there, and the plus sign there is just. So if you take the vector 1, 0, it rotates to the vector cosine theta, sine theta. If you take the vector 0, 1, it rotates to minus sine theta, cosine theta, which is perpendicular to it. So it will rotate something looking like this to something looking like this, where this is an angle of theta, and this will be 90 degrees. So this is a rotation. So let's say I want to try to find an eigenvalue eigenvector. So choose your vector and rotate it by theta degrees. Are there any eigenvectors where you get back in the same direction after I take your direction and rotate it by theta degrees? What do you think?
Depends on your theta, right? Like if you're
Well, so let's say theta is, pi over 4. I'll rotate by 45 degrees. Is there any vector where when you rotate by 45 degrees, it's aligned the same way? Well, then what you're telling me is there's no eigenvectors. Shouldn't this matrix have at least one eigenvector?
Well, what if you go, you rotate halfway and then take.
What is this halfway? I've applied the transformation. I can't apply half of the transformation. I rotate my vector 45 degrees.
Right.
No, right would be 90 degrees. I'm only doing it 45 degrees. Is there any vector whose direction is unchanged? And I just rescale the magnitude. But when I calculate the determinant of A minus lambda I, I'll get some roots, right? So shouldn't there be some eigenvector? Right, the fundamental theorem of algebra says there's going to be 2 roots to this. They could be repeated, I don't care. But there's got to be some roots. That root will have an eigenvector. What's going wrong? So what is the subtle thing you've all assumed? What kind of numbers do you think the eigenvalues might be for this? Complex. What might be true about the components of your eigenvector? Complex. Just because I have real components in the matrix does not mean that my output is going to have, that my eigenvector is going to be real. So you always want to look at when are you closed. If you're looking at solving polynomial equations over the integers do not necessarily have integer solutions. Over the rationals do not have rational solutions. Over the reals do not have real solutions. But over the complex, all the roots are complex. That's what's great about the complex numbers. So unfortunately, this could have complex eigenvalues, and it could have eigenvectors with complex components. So as a nice exercise, you should find the eigenvalues of this matrix. You should find the eigenvectors of this matrix. If you were doing homework problems, that would be one of the ones. Strongly urge you to make sure you can do something like that and see what they're like. You have some idea of what the eigenvector must be, though. So we know that this is rotating by 45 degrees. How many times do you want to apply this matrix?
4 times.
Not 4 times. Well, 4 times is not horrible. 8 times, right? Because if you apply this matrix 8 times, what do you get? You get what? Yeah. Now that's interesting. You should be able to deduce something from this. If I apply this matrix 8 times, what is it? What matrix must A be? It's the identity. This is the case when theta equals 45 degrees. So if I have eigenvalues, if AV equals lambda V, then A to the 8V is lambda to the 8V is V. What can you conclude about lambda to the 8? It's 1. So here's a nice hint in terms of trying to figure out what the eigenvalues are for this matrix. Now, lambda to the 8 equals 1 has 8 roots. This only has 2. But this gives you some information. Okay. So we're making progress. We know that if our matrix is real symmetric or complex Hermitian, it has real eigenvalues. So what we want to do now is we want to show that any real symmetric or complex Hermitian matrix can be diagonalized. Do you remember this proof? Or at least the statement. Any real symmetric matrix can be diagonalized by an orthogonal transformation. All right, do you remember what an orthogonal transformation is? So Q is orthogonal, I'll say real orthogonal, if Q transpose Q equals Q transpose is the identity. U is unitary if U Hermitian U equals U Hermitian is the identity. So the way you should view so here's Q transpose, here's the vector Qi, here's Qj transpose. And what this is telling you is if you take the ith column of Q and dot it with the jth column of Q, you get 0 unless I equals j, in which case you get 1. So it's basically telling you that the vectors of Q are an orthonormal basis. So vectors of Q are an orthonormal basis.
Don't you need orthonormal there also?
I'm sorry?
Q is orthonormal if Q transpose Q equals identity, not orthogonal.
What are you saying I need?
Instead of orthogonal, orthonormal.
We call Q an orthogonal matrix.
Okay.
So the notation is Q is orthogonal if this condition holds, Q is unitary if this condition holds. So technically, you could have maybe something other than just identity, but we always assume when Q is orthogonal, we mean this. So we mean a matrix whose columns have absolute value 1 and are mutually perpendicular. All right. So what we want to do is we want to prove that a real symmetric matrix can be diagonalized. So we're going to start with something simpler. We're going to start with the trigonalization lemma. So this is one of my favorite lemmas in linear algebra. It says basically any matrix can be put into upper triangular form. There are people who like lower triangular form. For the most part, they have been beaten down and are in hiding. They are mostly gone at this point. Okay? You might as well choose the convention, and everybody might as well work the same way. So no matter what, you could always find, given there exists an invertible S such that SA, I always forget which side we want to put the inverse on, doesn't really matter, just exchange S and S inverse equals T, where T is upper triangular. Okay? So this is a nice result. Any matrix can be put into upper triangular form. Let's do a corollary of this as motivation. Corollary. Assume A equals A transpose, so it's real symmetric. Then T is diagonal. Okay. So we'll get to that later. So let's prove the upper triangle, and I might need to prove a little bit more about S to get the inverse I want, because the S I want, I might actually want S to be orthogonal, and so I might actually need a little bit more here than just a generic S. So let's prove the triangular lemma. Since A is a matrix, has an eigenvalue eigenvector. Now, by the fundamental theorem of algebra, it has to have n eigenvalues if it's an n by n matrix. It might only have one eigenvector, but it's got to have at least one. So we can say A v1 equals lambda 1 v1. Okay? So what I want to do now is I want to take my matrix and I want to build it up in a nice way, and change my basis to incorporate V1. And what I want to do is I want to start and I want to build some kind of nice matrix. So let's use Gram-Schmidt. Without letting you know, we can assume the length of V1 equals 1. Use Gram-Schmidt to make an orthonormal basis with V1. Okay? So basically you take the directions, E1 through En, put in V1, and now there's going to be a linear combination of V1, E1 through En, and now I can replace En with that linear combination. Or, well, I first have to go through in stages. I take V1, I put in either E1 or E2, swap things out, use Gram-Schmidt orthonormalize, or just take directions perpendicular to it. Lots of different ways we go. Is everybody comfortable that I can complete and form a basis with V1? So we'll call that matrix Q, or we'll call this Q1. So here is V1, and then we'll call it, Q12, Q13, Q1n. Okay. And so now, let me look at Q1 transpose A Q1. And let's apply the vector E1, which is just 1 followed by zeros. Well, if I take the matrix Q and I put on the vector 1 followed by zeros, so this would now become Q1 E1. What is Q1 E1 going to be? So when I apply Q to the vector 1 with all zeros, what vector do I get back? I just get back V1, and then A of V1 is just lambda V1. So this is going to just be Q1 transpose of lambda V1. So it's just going to be lambda 1 V1. So just lambda 1 Q1 transpose V1. So we've got, back over here. Let's recap. We have Q1 of E1 is V1. So E1 is Q1 transpose of V1. Right? Yes? Just apply.
And we know that Q1 transpose is the inverse because they are orthogonal.
Because they're orthogonal. We've constructed Q that way. So now we know Q1 transpose A, Q1 acting on E1. This was just lambda 1 Q1 transpose V1. But Q1 transpose V1 is just E1. So this matrix Q1 transpose A, Q1 acting on E1 is just lambda 1 of E1. So if you look at this matrix, whatever this matrix is, Q1 transpose A, Q1, when you put in the vector 1 with all zeros, you get back lambda 1 and then all zeros. What does the first row of this matrix have to look like?
First element has to be lambda.
First element has to be lambda 1. And what else is true about the rest of the first row?
It's all zeros.
It's all zeros. So we know that this first row is just all zeros. Okay? And now what we can do is we can keep playing this game. Is we can now look at what's going on down below. And then we can form a vector, Q2. And then we can make a new matrix, and we can keep pushing in the zeros further and further down. Now, if your original matrix A was real symmetric, Q1 transpose A Q1 is also real symmetric. So if this is all zeros here, this will be all zeros up here. So if we want to just work in the special case when things are real symmetric, if our matrix is real symmetric, since A equals A transpose, Q1 transpose A Q1 equals Q1 transpose A Q1 transpose. So that matrix has to look like lambda 1, and then all zeros here, and then gobbledygook. And now what you do is you lather, rinse, repeat. Now we play the same game over here. And this is now an n-1 by n-1 matrix. So this matrix has an eigenvalue. And that matrix eigenvalue will have an eigenvector. And then we can form a new Q2. And then what we'll do is for the Q2, we'll do 1, all zeros, and then we'll shove Q2 down there like that. And then you just keep playing like this, and at the end of the day, you'll have a diagonal matrix. So this proves that a real symmetric matrix can be diagonalized, and can be diagonalized with an orthogonal matrix of Q's. Okay? You could prove the triangularization lemma that any matrix can be put into upper triangular form. I have tweaked the proof, so rather than proving the theorem because we were running out of time, I went straight for the result I care about. But as a nice exercise, modify this. So that would be another good homework question or a good exam question. Modify this argument to show any matrix can be put into upper triangular, or if you want to be different, lower triangular form. And now we know an enormous amount about our matrix. That a real symmetric matrix is a diagonal matrix with some kind of rotation in terms of the axes. So there's really only n independent quantities. There's the orientation of the axes, but once you choose your axes appropriately, there's just n basically stretching factors. That's incredibly powerful. So an n by n matrix could have n squared parameters. So then the question becomes, how many parameters must be in this matrix Q? Well, it's got to be n squared minus n. And then you can think about how many different angles you have. And so when we get into random matrix theory, we will be concerned not with the matrix Q, but for each transformation A, we'll be concerned with the lambda. We'll be concerned with the diagonal part. That's the part that matters. The rest is just how you orient your coordinate axes. We don't care about that. All right, so this is a good place to stop. For Friday's class,